Hello everyone. Today's lesson is going to be on simplifying radicals and roots. Now, to start, before we get into how to break those down, I did want to show this list of perfect squares and perfect cubes. This list is going to be huge in being able to break down and simplify those radicals and square roots and cubed roots. Just knowing what perfect squares are and perfect cubes are will allow you the opportunity to split things up, break things down, or even just straight out solve a problem. What you will notice is that these numbers will keep popping up over and over and over again, and by knowing what those numbers are, it will make things a lot easier for you to break things down. So, whenever we do the problems today, we're going to see these numbers pop up, and that's just going to be how you can relate what you see here to what we see in the problems. But my best advice is to write this down and have a copy for yourself, but probably even better than that is just to memorize the first 20 to 25 perfect squares and the first 6 perfect cubes, because those numbers will come up over and over and over again. Okay, so our first set of problems here are just entry-level problems into how to solve radicals. Now, if the numbers were perfect squares or perfect cubes, you would just get a whole number answer out. When they are not, you have to break each radical down into smaller parts. Now, our goal for today is to break a radical down, and I'll write this here. The goal is going to be break the radical down into 2 parts. The first part should be a perfect, if I could spell, perfect square or a perfect cube. The second part should be whatever is left over. So again, our goal today should be breaking things down into 2 parts. The first part is a perfect square or a perfect cube, and the second part is just going to be whatever is left over. As a general rule of thumb, or maybe a trick if you want to think of, the leftover part is usually going to be something like 2, 3, or 5. And you'll see what I'm talking about with that as we get into our problems. So, looking at number 1 here, we have the square root of 50. Now, we know we can't take the square root of 50, so what we need to do is we need to try to break down 50 into 2 factors, right? Split it up, divide it. And when we do that, we are basically creating 2 separate radicals that will eventually be multiplied together. I need this first one to be a perfect square. So when I think about my perfect square numbers, I have 1, 4, 9, 16, 25. Right, those are my first 5. Well, out of those options, I know that 25 can go into 50, and 25 can go into 50 2 times. So you see, now on the left-hand side, I have a perfect square. On the right-hand side, I just have whatever's left over, and that does happen to be a 2, a 3, or a 5. Now, I will say just off the beginning, the 2, 3, or 5 is not a hard and fast rule. It's not like always going to happen, but you have a high probability of things working out in your favor if that's the case. So, I've accomplished my goal. I've split up 50 into 2 parts. I have a perfect square and a leftover piece. Now all I have to do is take the perfect square. So the square root of 25 is 5. Let me switch to a pen. Is 5. And then the square root of 2 nothing happens to it, we just rewrite it. And so now you've been able to take your square root of 50 and simplify it. All right, moving on to 45. So it's not a perfect square. We know we have to split it up into two parts. Start thinking about perfect squares that can go into 5, 1, 4, 9. Okay, 9 works, right? Because we know that 9 times 5 is 45. From here, we can take the square root of 3, and that square root of 5 gets rewritten. So again, just quickly, you got a perfect square, and then you got a leftover piece, which is easy, or not easy, it's still one of the 2, 3, or 5s. And the reason that I'm telling you and I'm pointing out the 2, 3, or 5 thing is just because when you're splitting up numbers, if you are dividing by 2, 3, or 5, you're kind of guaranteeing that you're getting the largest possible perfect square that you can get. And that just really helps. Okay, so now we go on to cube roots. Now, a cube root just requires a little bit of shift in thinking, right? So instead of thinking about perfect square numbers, we need to think about perfect cube numbers, right? Perfect cube numbers are like 1, 8, 27, 64, right? Those type of numbers. And can any of those perfect cubes go into 128? Well, even though I'm dealing with perfect cubes, my goal is still the same. I'm still trying to split into two parts. And now when I select my numbers, I want to select a perfect cube, and thinking about them, 64 can go into 128, and it can go into 128 2 times. So we know that 64 times 2 is 128. Notice that on the left-hand side, I have a perfect cube. On the right, I again have split up things into 2, 3, or 5. So that kind of helps ensure that I'm doing things right. Now it's just a matter of taking the perfect cube. Well, what's the cubed root of 64? The cubed root of 64 is 4. And the other leftover part just gets rewritten. And so we're done. So now what we have is, one solid way to break down radicals. It will take some practice, and you can see just through these first 3 examples that knowing how to solve a perfect cube, or knowing perfect cubes and knowing perfect squares really matters. All right, we're going to move on up to problems 4 and 5. So these problems do the same things as 1, 2, and 3, but now they ask you to add them together. The big thing that we have to remember here is that you cannot add radicals unless they are exactly the same. So some people would want to add the square root of 45 plus the square root of 500 and get the square root of 545. You can't do that. You can only add radicals that are the same and have the same number inside. So our goal here is to break down 45 and 500 so that they have the exact same number inside the radical. Well, when I break down 45, right, we know that that can become the square root of 9 and the square root of 5. We've already done that one above. And we know that that one simplifies to 3 square root of 5. So when I break up 500, the most important piece to me right now is to make sure I get one of those factors being the square root of 5. So when I split up 500 we could split up into 100 times 5, or square root of 100 times square root of 5. So then the square root of 100 simplifies to 10, and the radical 5 stays along for the ride. Now that I have matching pieces, and I'll highlight them, so we both have square roots of 5, all we have to do to solve is just add the numbers that are not in the radical sign. So 3 plus 10 becomes 13. The radical 5 just hangs out, and you get 13 square root of 5. Doing the same thing with cubed roots, you can do that. This time you just have to kind of think about what are your perfect cubes again and how we can split that up. Thinking about it, I can split up 81 into the cubed root of 27 and the cubed root of 3. I can split up 375 into the cubed root of 125 and the cubed root of 3. Now that's nice because you can see still we've got matching pieces here, which is our goal anytime we're trying to add or subtract crazy radicals. Then all we have to do is simplify. The cubed root of 27 is 3. That cubed root of 3 is along for the ride. Then we're going to subtract the cubed root of 125, which is 5. And then the cubed root of 3, again, is along for the ride. So now doing what we did last time, all I have to do is actually just subtract 3 minus 5. 3 minus 5 is negative 2. And then the cubed root of 3 is just along for the ride. Okay, now we're going to move on to the intermediate section. The intermediate section is only intermediate just because there are no coefficients or whole numbers that we're dealing with. Everything is a variable and an exponent. Before we get started in this section, I do want to point out a term, and that term is called index. I've highlighted one. Now I'm going to write it. Index. The index is going to let you know what type of root you are taking, right? If it's a cubed root, a fourth root, a fifth root, then that is going to be written right in that little nook of the radical sign. If you notice that there is nothing written there, then that index is 2 because we have a square root. And essentially, it's a square root. The index is 2 because you're multiplying a number times itself. The index would be 3 for a cubed root because you're multiplying a number times itself again. But that number is important, and it's important when taking these type of radicals because there is a cool property anytime you're trying to take square roots and cubed roots of things, especially with exponents. The property says that you can rewrite the exponent or the whole radical as the inside exponent over the index. So again, it's the inside exponent, which I will highlight in green, and I'll do that for the first 3 here. It's the inside exponent over the index. And so in this case, for number 1, we just rewrite the problem as 4 over 2, and we know that 4 divided by 2 is 2. So your final answer for number 1 is y squared. And we get that just by being able to divide those two numbers and get them in the right order. For number 2, right, we can rewrite that as x is equal to 8 over 2. Again, you get the 8 from the inside, you get the 2 from the index, and then you simplify. 8 divided by 2 is 4, and you've gotten your answer. With cube roots, they're exactly the same. There's no difference there. All you have to do is rewrite the problem as 12 over 3, and 12 over 3 is 4. So these are not as bad, and at first glance, you look at those and you're like, hey, those might be a little more straightforward than the ones we've just got done completing. The problem comes when they don't work out evenly. What do you do? Well, we still know we have to split it up, right, into 2 parts, but now our 2 parts, the first part, it needs to divide evenly. The second part is going to be whatever is left over. So now when we are splitting up exponents and variables with exponents, we're splitting it up into 2 radicals. The first part has to go evenly, and the second part is whatever is left over. Now, what's nice about square roots, so looking at examples number 4 and 5, the easiest way to handle that is just to take one off of the exponent that you're given, so that way you have an even number, because we know any even number can be divided by 2. So here, if I do that, I can split up y to the 5th into y to the 4th times y to the 1st. The reason that I can do that is because when you're multiplying exponents, you just add them. So 4, which I'll highlight here in green, 4 plus 1 is 5. And that's how exponents split up. So all you have to do is just take one away, and you'll be in good shape. Because then at this point, as I scroll up, at this point, the left exponent can become 4 over 2. And the right exponent we can't, or the right radical we can't do anything with, so we just leave it. Notice right here, I also did not write the exponent of 1, and that's just because you don't have to. If you want to put that into your problems, you absolutely can. I would just not expect to see that in textbooks, in worksheets, on quizzes, online, anythings. You just, a lot of times, anytime a 1 is involved with things, it won't be written. So just know that you can do that. Continuing on with our simplifying process, we know 4 divided by 2 is 2, so we get y squared from the first radical, and the second radical just stays the same. Now, I completely understand that this looks like a mess, but this is the correct answer. It is acceptable. Your goal here is not to get just one thing out. Your goal is to break down the radical into its simplest terms, and this is what's considered simplest terms, because you've been able to get out a term that's out in front of the radical, and you have just a leftover piece left inside. All right, we have 3 more examples, so we're going to do the same thing on all 3 of these, starting with number 5. So number 5 is a square root again, so we split that up into 2 parts. Remember what I said, the easiest thing to do is just take one away here for square roots. That leaves me with x to the 10th and x. We can rewrite x to the 10th as x to the 10 over 2. That's just another way to take that radical, which simplifies all the way down to x to the 5th. We know that our square root of x, nothing can happen to it, so all we have to do is just bring it down, and we've simplified our answer. Moving on to problem 6 and 7, notice that we are using cubed roots, and so our first part, which I want to kind of highlight and just draw your eyes to, the first radical that we create needs to divide evenly. So what I have to do is I have to think about something that goes evenly, that 3 will divide evenly into. So I think about my multiples of 3, right? I've got 3, 6, 9, 12, 15. I want to choose the largest number that does not go over the exponent I'm given. So if I'm thinking about my multiples of 3, 6, 9, 12 is the largest thing. So when I split up my exponents, I choose y to the 12th, and then what's left over is y squared. And again, I know that because 12 plus 2 is 14. Again, since I chose that multiple of 3, that lets me rewrite the first exponent as, need to go back, forgot my cubed roots, gotta have those in there. That lets me write my exponent, or my radical, as 12 divided by 3, which ends up being 4. And then this piece, the leftover piece, just gets rewritten. So, as we've broken down y to the 14th, we broke it down into y to the 12th, because I know 3 can divide, or 12 can be divided by 3 evenly. and then the leftover piece, which is y squared. I simplified the radical to 12 over 3, and 12 divided by 3 is 4, and then the y squared just stays the same. All right, so now we're going on to the last example here for number 7. Number 7, we're doing the same kind of deal, right? I need to create two radicals, and these cubed roots here, right? I need to split up 22 into something that divides evenly and whatever is left over. So I think about my multiples of 3. Since I'm taking a cubed root, I've got 3, 6, 9, 12, 15, 18, 21. 21 is the closest I'm going to get to 22. So that gives me m to the 21st power in one, and then just m in the other. That allows me to rewrite the first radical as 21 over 3, which simplifies to 7. The second radical we know nothing happens to, so we just rewrite it, and we are done. So this process is how you take care of exponents and variables with exponents inside of radicals. And now we move on to our advanced problems. Now these problems are actually not any harder, they just have more parts. They're basically combining square roots and cubed roots with coefficients alongside square roots and cubed roots with variables and exponents. The way that I handle these problems is to break it down into smaller pieces, because sometimes people look at these problems and they just think, oh my gosh, it's too much, I can't handle it, like there's so much going on. But if we break it down into smaller pieces, we're actually able to solve the problems really quick. So first thing, in example number 1, I see that I have my first part that is this, it has a 16, it's a coefficient of 16, and the second part, which has our variable, which is y to the second power. For me, when I go to solve these problems, I just break them down into those parts. The first part that I'm going to take care of is just the square root of 16. I'm not worried about anything else. I know that the square root of 16 is 4. The second part that I'm going to take a look at is the square root of y squared. We know that the square root of y squared can be written as y 2 over 2. And we know that 2 divided by 2 is just 1. So by solving both parts separately, we're able to get our final answer, which is 4y. All right, let's see how that works on 2 and 3. So starting in problem 2 here, we have the cubed root of 8. So that gives me the cubed root of 8 as a place to start. I look at the cubed root of 8. I know that the cubed root of 8 is 2. And then I can move on to my variables and exponents. At this point, I have the cubed root of y to the third power. I know that the cubed root of y to the third power can be written as y to the 3 over 3. And I know that 3 divided by 3 is 1. So my final answer for problem number 2 is 2y. Moving on to number 3. I can do the same thing. I know it looks a little different because we have different parts here, but what's nice is even though we have different parts, I can still separate each variable as its own little mini problem. And so I'll start by doing that. I have to take the square root of x to the 4th power. Well, the square root of x to the 4th power can be written as 4 divided by 2, and we know that 4 divided by 2 is 2. I come back to the square root of y to the 8th. I can rewrite that as 8 over 2, and that just becomes y to the 4th power. So my final answer for number 3 is x squared y to the 4th. Now, As we move on through our problems here, you'll see that there are some that become a little more complicated. We know by now that we've run into some that work out evenly and some that don't, but again, that doesn't really matter. Our goal is just to break down our problem into as many smaller parts as we can possibly get. And if we do that a section or a piece at a time, we're going to be okay. So, taking a look at problem number 4, we're going to start with just our number, right? And the only thing that we're worried about is the square root of 256. Well, I know that the square root of 256 is 16. So I'm good there. Now, I have to move on to my variable in the exponent. Well, we've encountered this before, and if we remember, whenever I have the square root of y to the 5th, I have to break it down into 2 parts. One part that's divisible by 2, one part with everything that's left over. So that gives me y to the 4th power and y. I know that y to the 4th power can become y squared, or the square root of y to the 4th power can become y squared. And then we have our leftover piece of square root of y. Again, this looks like a little bit of a mess, but you're okay. This is a correct answer. Right? Breaking that down again, I took the square root of 256 to get 16. I took the square root of y to the 5th, split it up into 2 parts, took the square root of y to the 4th to get y squared, and the leftover piece just got rewritten. And that's how you solve those. Now, the crazy thing is that this kind of stuff can happen in a lot of different ways, right? So we got to be ready for how this occurs. Like, for example, in our next problem, we have a cubed root that we're dealing with. So we're going to start with the cubed root of 64. Now, luckily for us, the cubed root of 64 does work out to be 4. And so now what that leaves us with is we got to deal with the cubed root of x to the 13th power. So the cubed root of x to the 13th, remember when we're dealing with cubed roots, I need the first part to be able to be divided evenly by 3. So I think 3, 6, 9, 12. 12 is the largest one I can choose, so that's going to give me the cubed root of x to the 12th power. And the cubed root of x, that's how I'm able to split that up. Remember that x to the 12th, the cubed root of that can be written as 12 over 3, so that's just x to the 4th, and then the remainder piece is just left over. So my final answer here, and I'll write it just over here to the side, and I'll write it in red so you can kind of see. Your final answer is 4 from the 4 we got from the coefficient, and then all that we simplified everything else to. So that's 4 x to the 4th power cubed root of x. Now, again, I understand that those look kind of crazy, but it's okay. All right, so now we're moving on into some other problems, and these last two might have a little bit more complication to them, but it's fine. Like I said, all we're going to do is we're going to do smaller radical simplifications, and then we're going to be able to write our answers together. So the first thing here is I have 32, and I need to take the cubed root of 32. So I start and I take the cubed root of 32. Well, there is no perfect, 32 is not a perfect cube. So I need to split that up into a smaller piece. The way that I can split that up is the cubed root of 8 and the cubed root of 4, because 8 times 4 is 32. We know that the cubed root of 8 is even, that's 2. And the cubed root of 4 is my leftover piece, so it just is what it is. The next part of the problem that we have to deal with is x to the fourth power. X to the fourth power, taking the cubed root of that, we have to split that up into x to the third. Let me zoom in. X to the third and x. So we know that the first one does simplify, so 3 divided by 3 is just 1, so that's just x. The cubed root of x is our leftover piece, so we just rewrite it. Okay, and then now we're on to our last part. Our last part here is y to the sixth, and if we're trying to take the cubed root of y to the sixth, lucky for us, this one does divide evenly. 6 over 3 is y squared. Now, we've been able to simplify all of our parts, right? First we took care of the coefficient, then we took care of the x's, now we've taken care of the y's. So it's time to write everything down, but we need to make sure we write everything down in order. Notice that we have what I like to call, and I'm going to put this in baby blue, outside parts, like the 2, the x, and the y squared. And when I say outside, what I'm really talking about is they're not underneath the radical. When I say underneath the radical, you see I have a cubed root of 4 and a cubed root of x. So as I've simplified, I have actual numbers, whole numbers, complete variables that are not inside of a radical, and then I have some that are inside. When we go to write our answers, we have to write everything that's outside the radical first, then put everything inside the radical. So, doing that, outside the radical, I have a 2, I have an x, and I have a y squared. So that's where I start. So I've used the 2, I've used the x, I've used the y squared. Now, the only parts that are left are the 4 and the x inside the cubed root. So I just make one big cubed root and do the 4 and then the x, and then I'm done. So I wrote all of my outside pieces together, all of my inside pieces together. And after all that, we are done with simplifying that kind of radical problem. All right, one last one here is we have the square root of 288 x to the third, y to the fifth. So this one starts out the same. We're going to first look at 288, then we're going to look at x to the third, then we're going to look at y to the fifth. So we start by taking our square root of 288. Well, 288 is not a perfect square, but we can break that down into 144 and 2. The square root of 144 is 12. The radical 2 is our leftover part, so we just rewrite it. Moving on to our x's, we have x to the third power that we're taking the square root of. That doesn't work evenly, so remember all we have to do is just take one away to get x squared and x. X squared can be written as 2 over 2, which ends up being just x. The leftover piece just gets rewritten. Moving on to our last part, which is y to the fifth, and we are trying to take the square root of y to the fifth. Well, y to the fifth doesn't work evenly, so we just take one away, y to the fourth, and y. Y to the fourth can be written as 4 over 2, which ends up just becoming y squared, and our leftover piece just gets rewritten. Now it's time to write our answer in final form. So note that we have a square root of 2, we have a square root of x, we have a square root of y all inside the radical. But we start with our pieces that are outside the radical. That's 2x and y, or 12x and y squared. So I start there, 12x y squared. I've used those pieces. Then I create one big radical, and then I do 2, then I do x, then I do y. And now you've gotten your final answer. Guys, I hope this lesson has been helpful and you've been able to see plenty of examples of how to solve and simplify radicals, some that work evenly, some that don't. But also, going back to the very first thing, I hope you take seriously understanding and knowing and having your first 20 to 25 perfect squares and your first 6 perfect cubes, because they will pay off when you're trying to do these type of problems. Thanks for watching. Please like and subscribe, and if you have any questions, please let us know in the comments.